So, our second skill in our seventh learning unit on quantum theory and atomic structure has to do with this quantum theory part. And really, all this is having us think about is figuring out where electrons are in atoms, right? And maybe you've learned about in another science course that electrons just kind of circulate around an atom, and that's absolutely true. But we want to know it to a little bit more certainty, be able to think about it a little bit more specifically. So we're going to go into some detail in this learning unit here. So I'm not going to go into a lot of history, but here's some really important scientists that have had sort of critical pieces and components to this. Some of them you've probably heard of, right? Here's Albert Einstein, right? He's infamous for his E=mc² equation, among a whole bunch of other things. But really, that equation tells us that matter and energy are alternate forms of the same entity. Now, don't worry, I'm not going to quiz you on anything about the history, but I just think it's interesting to think about sort of the shoulders of these giants that we're standing on to be able to understand what we do now. So Louis de Broglie had some important contributions in thinking about the wave nature of electrons, right? So here's an important equation that has to do with the wavelength of particles. And so again, we're not going to go into too much of any of these individual scientists' work. I am going to talk on the next slide a little bit about Werner Heisenberg. Basically, all of his work allowed us to think about the fact that we can't simultaneously know the position and the speed of an electron. So an analogy I'm going to have you think about as we think about where electrons are is I want you to imagine a large football stadium, right? Like, Heinz Stadium in Pittsburgh, or something that's very, very large. And I want you to imagine a pea, like a little vegetable, a pea, sitting on the 50-yard line. That represents the size of the nucleus of an atom. And the size of the entire stadium represents the space that an electron has to roam around. So imagine if you had to find an electron that's even smaller than a pea, and it could be anywhere in that stadium, right? Got a lot of space that you can move around. So I want you to have that analogy as we sort of think about where electrons are. So why all the work of these scientists is important is Heisenberg came up with what he called the Heisenberg uncertainty principle. Again, saying we can't simultaneously know the position and the speed of an electron. And I'm not going to go into the physics of why that's important. But I do want you to understand that electrons are what are important for the shape, and shape is what affords the function of molecules, and then reactivity. So we want to know where electrons are, because that can tell us the shape of molecules, and that's important for thinking about their reactivity in terms of specific atoms. So the truth here, and all that we really need to think about, is that we can only know an electron's position within a certain probability. And probability really means math. And so we can use equations. So we can use equations to define the probability of where we could find an electron, and we call these wave functions. So when you think about atomic orbitals, and you guys have seen sort of the cartoony representations of atoms, and they show orbitals almost looking like they're rings on a planet, right? Those represent sort of the probability of where we're going to find an electron. And I just kind of want to highlight just a difference in semantics. When you see those little cartoony representations and they show what looks like a circle, or where that electron is traveling, that's called an orbit. That's the path of an electron around the nucleus. But again, it's zipping around looking at all different spots, right? The orbital is that mathematical function that describes where they might be, that path that they've taken. Okay? And so one of the things that I'll imagine us thinking about is taking a time-lapse picture of those orbits, of where that electron might be traveling, where that electron might be running around in our stadium. And that time-lapse picture represents what we call an electron density diagram. So it's, again, the probability of finding an electron in a certain volume. So these, again, don't worry about these pictures too much, but these little blue dots each represent a snapshot of where an electron might be at any given time. Okay? And it has to do with, making sure that they don't travel someplace that they're not allowed, that they're in a good energy space, all of that stuff. But when we kind of put all of this together, we get what we call a cloud, an electron cloud. And that really represents a probability of where we're likely to find electrons. So that's all I want you to think about when we see these pictures, these cartoons that show electron clouds. really what we're just looking at is, here's the probability of where we're likely to find an electron, right? Again, if we're back in our big football stadium and we've got electrons zipping around, maybe we might see a cloud that sort of represents the region that they're likely to be. And as we noted kind of when we talked about some of our stuff last time, let me just flip back here for a second. There's going to be spots where you're not likely to find an electron, where there's orbitals that don't have probability, right? So just think about this when we see these cartoons. These really represent the probability of finding an electron within that space. Okay, so what's the skill that we need to know? That was sort of the qualitative stuff. What's the skill that we need to know how to do from this chapter? Okay, so we're going to start this in this learning unit, and we're going to build on it in our next learning unit. It's assigning quantum numbers. So really all this is kind of a coding system, COD, a coding system for identifying where electrons might be. And right now we're learning 3 out of 4 pieces of the code in this learning unit. We're going to learn the principal, angular momentum, and magnetic momentum quantum numbers. You don't need to remember those names. Just remember that they're N, L, and M sub L. That's how we'll refer to them as. Okay? So here's some basic things to think about with these sort of quantum numbers. This N you can think of as relating to the energy of the orbital, and it is directly related to what row we are on the periodic table. Okay? The angular momentum, this L, okay, this has to do with the shape of the orbital, and maybe you've done some work in another chemistry course where you've heard of S, P, D, and F orbitals. It has to do with assigning those, and we'll talk about that in an example problem I'll do on the next slide. But it's important to remember that there's certain allowed values in our code. So N has to do with the row on the periodic table, so it can go 1, 2, 3, 4, and so forth. Okay. L has to do with an integer value that's going to be between 0 and n minus 1. So just as a quick example, and we'll do another one on the next slide here, if we're talking about things that live in the second row of the periodic table, elements that live in the second row, and we're talking about the orbitals where n equals 2, second row, okay? That means the values that are allowed for L are 0 and 1, because we stop at n minus 1. So those are the allowed values for L, okay? Then we've got M sub L. This has to do with the orientation of the orbital. We're not going to do too much with that right now, but I do want you to understand where allowed values are. So values for M sub L are going to be integers between the allowed L values, minus L to plus L, and including 0. So let's go through our example that we just had there. If n equals 2, then the allowed values for L are 0 and 1. And I'm going to highlight here that those values of 0, 1, 2, and 3 define these different shapes. So an L of 0 is an S shape, an S orbital. An L of 1 is a P orbital. An L of 2 is a D orbital. And an L of 3 is an F orbital. So let's go through this example again. If n is equal to 2, the possible orbitals we could have are S orbitals and P orbitals, because the possible values of L are 0 and 1. Now the possible values for M sub L, now we have to kind of divide that out per the orbital. The possible values for that S orbital are only going to be 0. Right? That integer value is going to be 0 because we're minus L and L. If L is only equal to 0, then it's going to be 0. For the P orbital, the possible values are minus 1, 0, and plus 1. We've got 3 options. So this kind of explains it a little bit further down here. So this is a table you can use as you're sort of working through this coding system. If n is equal to 2, then L could be equal to 0 or 1. If L is equal to 0, the only possible options for M sub L are 0. But if L is equal to 1, then the possible options for M sub L is minus 1, 0, and plus 1. And why this is also important is we're going to get to this on the next slide. The number of M sub L's that you have tells you the number of orbitals you have. So we can look at the number of these, and this is going to be equal to number of orbitals. Now what I mean is you actually count the number of numbers. So there's 3 numbers there, so there's 3 orbitals, right? 3 numbers is going to be equal to 3 orbitals. So we'll see this. I'm going to go through a couple of brief examples here, the 2 kinds of problems you might see. One is telling me what might be wrong with the set of quantum numbers, so what's wrong with the code, and another one is assigning the code. So maybe you've seen pictures like this. I just kind of wanted to highlight, when we see s orbitals, they look like spheres. You can remember that s is for a sphere. P orbitals are kind of pear-shaped, so they kind of look like these pear-shaped lobes. D and F orbitals get complex, so don't worry about those shapes, but we're going to build on these shapes at the very end of this course when we start thinking about the shapes that molecules have. Okay, so we're going to get to that at the very end of this course, so I wanted to just kind of introduce it right now. But let's go through a couple of examples here. Again, the 2 kinds of problems you're likely to see. The first one here is, show me what's wrong with these numbers. You know, here's a code, tell me what's wrong with it. And then the second kind of problem is, tell me what the code is, derive the code. So let's go through this first one, which is a little bit simpler, I think, to think about. If we've got n equal to 1, so remember, if n is equal to 1, this is the row on the periodic table. So we need to then move from this and then say what are possible allowed values. Well, if n is equal to 1, the only allowed values for L would be 0 to n minus 1. Well, n minus 1 is 0, so the only allowed value is going to be equal to 0. Remember, we can define that as being an s orbital. So right now, we're already seeing that this is something that's wrong. This is a problem. We cannot have an L equals to 1. That won't work. Okay, so that's part of our code that could be problematic. If we look at m sub L's allowed values are it can run between minus L and plus L. So value of 0 is always going to be allowed. So this is going to be allowed. That's okay. But let's put this stuff together. All right. L equal to 1, there's a couple of ways that you could say that this code is wrong and try to fix it. L equals to 1, that's actually telling you you have a p orbital, which matches this. But if n is equal to 1, if we are on the first row of the periodic table, we're not allowed to have p orbitals yet. The only thing that we can have is an s orbital. So a couple of ways that we could fix this problem. We know that the code is wrong for a couple of reasons. If we're going to hold fast that n is equal to 1, then L can only be equal to 0. M sub L would be fine. But the name of an orbital that had n equals 1, that would be right. We'd have a 1 that would be there. This is right. So an L orbital of 1 or an L of 1 would be a p orbital, but you can't have this. So a way to fix this, right? So another way to ask this problem is, how could we fix this so that the coding could be right? We could change this so that n was equal to 2. If we made n equal to 2, and then we'd correspondingly have to change that to be 2p, then this code could be right. I know I'm probably kind of blowing your brain right now thinking about this. The only way to sort of get good at this code is to practice. So we're going to have time in class where we'll practice lots of problems with this code. But this problem, this first problem, was like, all right, tell me what's wrong with the code and then tell me how to fix it. All right, next kind of problem might be, all right, here's something that we're thinking about. You write the code. So we want to know what are the values if we're going to have n equals 3. So that's the only piece of information that they give us. They tell us that n is equal to 3. Okay, remember, we kind of move through this progression. If we know what n is equal to, we can figure out the allowed L values. So for L equal to 3, for n equal to 3, we could have L equal to 0, L equal to 1, or L equal to 2. L is always equal to 0 to n minus 1, whatever that value is. So n minus 1 is going to be 2 here. So our allowed values are L equals 0, L equals 1, and L equals 2. I'm just going to highlight here, L equals 0 is going to be an s orbital. L equals 1 is a p orbital. L equals 2 is a d orbital. Okay, so now we need to figure out the allowed m sub L values. So this is where it gets a little bit, it can get a little bit messy, because for our L equals 0, the only allowed m sub L values are equal to 0. For our L equals 1, remember that M sub L can run between minus L and plus L, including 0. So our possible M sub L values there are minus 1, 0, and plus 1. Our possible M sub L values when L equals 2 is minus 2, minus 1, 0, 1, and 2. So we've got a lot of options if we are living in the third row of the periodic table. So this problem is asking us to find the values, the allowed values of the L's and the M sub L's, and we want to know how many orbitals are allowed. Okay, so this is where I'm going to kind of come back to what we were talking about here. We're going to count the number of M sub L's that we have, and that tells us the number of orbitals. Okay, so stick with me here. And maybe you've learned something before. This is going to kind of lead into some things we're going to do in our 8th learning unit. So let's see what happens here. There's one number that's here. So we have one orbital that we have here. So this is going to be an s orbital. When we have L equals 1, M sub L equals minus 1, 0, and plus 1, there's 3 numbers here. So let me put here, we have one number. We've got 3 numbers here, so that means we've got 3 orbitals, and we've got 3 p orbitals that we're going to have here. Okay, this 3, just to highlight, this 3 is not that 3. Okay, now for here, we've got 5 numbers, so we're going to have 5 orbitals. So there are 5 possible d orbitals. Okay, I'm going to give you a preview for something we're going to see in our next learning unit here, okay? And maybe if you've taken an advanced chemistry course in high school, you maybe have seen this already. So this is new stuff, but I just kind of want to give you a little bit of a preview here. Each orbital holds 2 electrons, okay? So there's 2 electrons that are here. We're going to have 6 electrons that are here. And there's going to be 10 electrons that are here. So I'm going to give you a preview of this, or I'm going to review something that you've learned already. If we've got an s orbital, 2 electrons. P orbitals, 6 electrons. D orbitals, 10 electrons. This has to do with where we find things on the periodic table, or if you've done things with electron configurations. I'm going to say something that maybe will dust off some cobwebs or refresh your brain. 1s2, 2s2, 2p6, 3s2, 3p6. That has to do with what we're seeing here. And if that was a little bit confusing and totally Greek to you, don't worry. That's where we're getting in our next learning unit. But if you've heard about that before, that's how these next 2 learning units are going to tie together. And so we're going to see kind of some reinforcement of this quantum number stuff in our next learning unit as well. All right, so that's the end of our brief learning unit on quantum theory and atomic structure.